And we are live. Okay. So thank you for coming to today's event, and thank you for SOUR for hosting us. And today we have great presentations from EDF and SOUR and on topics related to industry optimizations and energy and resource optimizations. So we are very happy to be here. So who are we? We are PyLadies. PyLadies is an international group. I mean, there are meetups all over the world, and we are the chapter of Paris, and is organized by volunteers. So in 2 days, first we have the introduction by SOUR and PyLadies, then we have the application of machine learning algorithms to predicting leaks in pipeline by Sabrine and Maxime. And then we have improving energy efficiency of data centers through machine learning by Alain Yoch. And then we have cocktails and networking session. So I started this a bit earlier on the agenda. So we are PyLadies. PyLadies is the international community. We focus on Python and related tech topics. So it's for women and friends. It's not only for women, but we are trying and we would like to promote women in tech and their work and highlight their works. And it's run by volunteers. Sorry, I made a mistake. We have actually Chiara with us. So Maria, Chiara, and me, that we are based in Paris, and Maud that is helping us from distance. So couple of words on our code of conduct. Please be respectful, please be kind. And if you want to know more about it, you can look at the PyLadies code of conduct. And if there is anything that disturbs you or you don't feel comfortable, reach to us. And we either in French or English, and we will take it seriously. So we organize hybrid meetups, and we broadcast live. And let us know how it goes. And if you are interested to organize meetups, you can reach us on a Slack, on Twitter, and or just by our emails, paris@pyladies.com. And we are always looking for speakers, sponsors, for venues or goodies. So if you are interested, again, let us know. And EuroSciPy is happening in August in Basel. It's a really good conference. So if you're interested to join a conference related to Python and scientific Python, whatever, that's a good conference to be. And it's also financial aid is open. So if you're interested to join and would like to have a bit of help to get there, don't be shy, apply for financial aid and buy your tickets. So now I will pass the hand to our host. And just a couple of minutes. Sorry about this. I need to change this.
Thank you, Marta. So hi everyone, I'm Dalan and welcome to SOUR's place. This place is named Aquaverse by SOUR. So you know the name now. And it's a place that was built very recently in order to gather people that are focused on innovation and digital at SOUR here, and to do some presentation like today with you. So maybe some of you know about SOUR, maybe some don't know about SOUR. So let's check what you need to know about this company. So SOUR is a company of water. SOUR produces drinking water for you to drink, and also clean the wastewater you used. So to do drinking water, we need some factories. In fact, a lot of factories in the whole world. Those factories take the water from the water sources, like rivers, and do some treatment into those factories dedicated to drinking water in order for this water to be drinkable for you. So you drink the water, you use it to clean yourself, and for agriculture, they use it to grow some vegetables. And some industrials also use our water to do some product of daily life. When this water is used, it is considered dirty. Once it's dirty, we call it wastewater. And wastewater is also collected by SAWER in order to treat it and to make it clear, not clean, because we want this water to be clear enough to be returned to their natural ecosystem, so river again. And when you separate the clean water with the dirt, you have something that is remaining, and this thing is called the slug. In France, the slug c'est de la boue. And this slug is used after that to do some compost, for example, do methanination. So the cycle is here. One thing you could ask is, how big is SAWER? And SAWER is big enough to have offices all around the world. Here in the plain color, in blue, here, have a lot of places where we are working for you. And it's also small enough so that we can speak to each other all around the world with ease. So that's a good thing. For information, we are a lot of collaborators of persons, and we are doing some all our work for you. And you is 20 million of residents all over the world. So you see the dotted, that is where we deliver the water, drinking water, but also clean the water. And this is the number of drinking water we produce each year, about. So that's a lot. I didn't know when I was in SAWER for the first time. And this water that is drinkable run to you via those, this number is important for you to understand the next use case that will be presented. And this is the number of kilometers of drinking water pipes we have in SAWER, in all the world, many in France. And that's important because that is the data set of LeakFinder that will be presented to you. Yes, last but not least, each year, SAWER dedicates this number of millions of euros to just to do digital innovation. So that's why we are here. You're lucky. So in SAWER, we want to give the water the value it deserves. So that's why our projects are mainly focused on these three subjects. First, it is focused on resource protection. For example, we can do some use cases to detect if there is some kind of element that is too low or too high in our treatment plants. We focus on energy saving also. For example, we can predict when to shut down some treatment equipment in order to save energy, save electricity. And we also focus on performance optimization. So, for example, to detect exactly what are the sites that we need to do some maintenances very urgently. And for LeakFinder use cases that will be presented for you, the main subject that will be addressed will be this one. So resource protection and performance optimization. A word about our team. Our team is to industrialize data science use case in SAWER. So this is our team, and it's the team for SAWER, but all the group SAWER, the SAWER group, because we have some linked companies also, and we work with them also, some data scientists, for example. So the core team is composed of 4 data scientists, including 2 seniors. We have a product owner, a delivery manager, a security ops to help us have a good infrastructure, a secure one to work. We have a senior data engineer, and then we have our director. We have some partnership also with some schools and some other companies. Just one word about the ELO network of SAWER. ELO network is a network of SAWER dedicated to act for gender equality. Why is there this kind of network here? It's because in SAWER we know that gender diversity is key to performance for the company, for performance, but attractiveness also and innovation also. That's why the goal is to attract human talent and to change mindset inside the company, but also outside the company, for example, doing some presentation to schools, to little girls. And also to support female talent inside the company to go up to the highest management positions. And this is a serious story, this gender equality, because those acts about gender equality are evaluated into SAWER's direct indexes. For example, take this one, equality index. You can see that over the years, it is increasing, it is getting better. And for example, this other index, the representation of senior executive in SAWER, you can see that it also is increasing over the years. Before there were just 3 women among this number of persons, and now we are 11 women, and that's increasing. That's nice. So if you have some question about SAWER or ELO network, don't hesitate during the break. I can also say to you that there are open positions in SAWER, so don't hesitate to go to the site of SAWER. Those are open positions about a lot of positions, but also about IT position. For example, we are searching for our digital factory director, so don't hesitate, but there are also other posts, don't worry. So now please welcome Sabrine and Maxime for the next use case.
C'est ça, c'est de mettre en plein écran. C'est de mettre en plein écran.
Okay.
Ah oui.
That's enough. So, hi everyone. We are very happy to be here and to give this talk for the PyLadies community. My name is Sabrine, and I'm senior data scientist at SOAR. And joining me today, my colleague Maxime.
Hello, Maxime, data engineer for SOAR. Been here for 2 years now.
So with Maxime, we form a duo at the topic we will present to you, and we are a part of the data science team that Dalan has already presented. So let's dive into our topic for today. So today we are going to present to you Leak Finder, which is a machine learning-based solution to predict leak risk in water networks. Okay, so let's have a quick on the project timeline. So this project started in 2020. So we start by collecting data and doing the first exploratory data analysis. Throughout 2021, we focused on the modeling process and the machine learning part. In 2022, we transitioned to an industrialized mode using Dataiku. So Dataiku, it's a powerful data science platform that we will maybe present to you if we have time. And finally, this year, in 2023, we built a web application using Dash to provide our result for our colleague on the field. So you have to know that between all these steps, there were a lot of exchange, a lot of meeting, and also stopped period when we had to work on other projects, Maxime and me. So to give you a little context, pipe leaks is a pressing issue for the water sector companies around the world because it affects the efficiency of the water supply and have financial and ecological impacts. So in France alone, it's estimated that around 20% of the water supply lost due to leaks each year, costing millions of euros. And this is and this is have several impacts, starting by waste of resources. So what you have to know is that water, it's a resource that requires a lot of energy to be extracted, treated, and distributed. So when water leaks out of pipeline, it needs additional energy to be replaced. There is also ecological impact. So water leaking harm the local ecosystem and wildlife. So it can affect the natural waterways, and depending on the duration and the severity of leaks, it can cause soil degradation, soil erosion, and land degradation. So if a leak is in your, it will get worse. And there is also an important financial cost caused by pipe leaks. So in addition to all this impact, the traditional approach actually to find leaks have their limitation. Yes, and this is me and Maxime, and I will tell you a little about this photo. What I was saying is that a traditional approach to find leaks today have their limitation. It's estimated that it takes around 48 hours to a leak finder expert, we call them in French chercheurs de fuite, just to locate a leak. So they have many approaches to locate a leak. It can be a really basic approach, as you see in this photo. When the leak finder expert has just a metal stick that he put on the pipes just to listen to the water noise. They have, and it takes time. And they have also a more sophisticated approach. For example, they can put sensors in specific area and collect data about the water flow. But the more the approach is sophisticated, the more it costs and less it deployable everywhere. So as SOR is growing these last years, and the problem of managing the network grows too, and we needed a smarter and relevant solution, and this is how and why this project Leak Finder was born. Yes, so we faced four major challenges. We needed to recommend pipeline renewals, to prioritize leak detection effort, to implement predictive approach, and also to leverage our knowledge of the infrastructure by collecting field data. I'm talking about data. I think I will let Maxime.
Yes.
Yes.
So for now, the project is only deployed in France, using French data on our pipes and our interventions. But there are plans to deploy it in other countries where we manage networks, for instance, in Spain. And in France, we have about 900,000 kilometers of network, and 170,000 is managed by us. And so the efficiency of the network, as Sabrine mentioned, is about 80%, which means from all the water we put in our network, only 80% is consumed at the end, and 20% is lost by leaks. And so this is a map of the network efficiency. You can see that there are some disparities. For instance, in the West, you have very efficient networks compared to the rest of the country. And for us, we are trying our project in Agen here, which is a locality where the network is not very efficient, which means there is a lot to gain there. So as I said, 170,000 kilometers is managed by us. It's around 20% of the French network, and it's about 12% of the population. So in some, we manage networks mostly around smaller cities and in rural areas, because in the big cities, water is mostly managed by public entities. As in Paris, it's called Eau de Paris, which is an entity, a public entity created just to manage a network. And so the data in numbers, there are about 30,000 leak detection interventions, which is when the workers go on the field and try to look for the leak. We have around 20,000, this is per year. We have 20,000 leak repair interventions where we actually repair the pipes. And that means, considering we have around 4 million pipes, we have 0.5% of the pipes that have an intervention for a leak every year, which gets repaired every year. And so this is what we are trying to predict, a probability of the pipe having a leak in the following year. So about our data. So we split the data in two. We have the internal data, which is split between our asset-related data about the pipes, the age, the material, the length, the diameter, the pressure. We have some issues with data quality, which can pose some problem. And then we have the intervention data, which are the records of the works on the field that gets done every year. And then for the open data, it's mostly geographical. We have, for instance, the soil movements, which is the movement of the soil. And it's important because when the soil moves, it can damage the pipes. Same with the road traffic. With the vibration from the road, it can also damage the pipe. And also the presence of clay, argile en français, which means that when you have more or less humidity, the soil inflows or deflows, and it damages the pipes too. And so our internal data, it's provided by the collectivity with which we have a contract. So they provide data about the pipes of their collectivity. It's stored on our data lake. And then the intervention data, it's our colleagues on the field, they input the info about what they are doing on an internal application, and then we store it in our SQL databases. And then for open data, it's mostly public APIs. We have, for instance, the IGN or GeoPortail, which are government entities. And also we use Copernicus for the soil movement. Copernicus, it's a European program done to provide free data to the public to work on projects to protect the environment. So for this data, we use Python, some geospatial libraries, and also we use ArcGIS, which is a geomatic software to join our geographical data to our pipes. So the architecture of the project. So as Sabrine mentioned, we use Dataiku, which is a solution to implement machine learning programs from data ingestion to data preparation and also to publish web apps. So our data at SOR, it's stored on the Microsoft Azure cloud in SQL databases or in blob storages. Then for our exploration and data preparation, we use Python and PySpark. And for machine learning in this project, we only use scikit-learn. And then our web, it's deployed in Dash and Python. and it's deployed using Dataiku, which means it's pretty easy for us to maintain and run. And we also display our results on an internal application, which I will talk a bit later.
Yes. Okay. Okay, so how about our machine learning workflow? So we have built our approach on a classical machine learning workflow, ensuring that we use existing methodologies and not reinventing the wheel. So we conducted a literature review, and it was very hard to find studies that talk about machine learning and water use case in the same time. Sorry. So we finally selected the 3 studies that have the same goal as our project, or at least that have that use the same data. So we began simply by splitting the data using stratified sampling to be sure to keep the same distribution. We built a baseline. The challenge of the machine learning process was related to the metric. It was very difficult to find a suitable metric to evaluate our performance because, as Maxime said, we faced severe imbalanced data. So we have 0.5% of leaks each year that we want to predict. So it was very difficult to use classical metrics, like accuracy, recall, etc. Even F1 score or F beta score. I will explain why. For us, false positive and false negative are very important because if identify leaks that will not occur, it will lead to wasted time for the leak finder expert, and it will erode confidence in our tool. And if we not detect a leak, it will lead to waste of resource. So to overcome this problem, we worked with our hydraulic engineer expert, and we find business metrics that Maxime will present later that fit our goal. So what we did, yes, we just we benchmark several models. So starting by linear, non-linear, trees-based model boosting, we tried a simple deep learning architecture based on LSTM, but it was not relevant compared to the computation time. So we use simply a grid search and cross-validation to fine-tune our model using SMOT method to oversample and undersample the data. If I have an advice, just when you have imbalanced data, just focus on choosing the best metric to evaluate your model. So once the model finds, we retrain it on all the original data set. We score it by computing our business metric, and we did an interpretability study using SHAP value that I will explain later, and some statistical tests. Did I forget something about machine learning? No. Okay. No, deployment. Okay, so once the model has been chosen, we deploy it using Dataiku. So Dataiku, it's a very useful data science platform. You can write your own code, or you can use Dataiku to do AutoML. So we benchmark the tool in the team, and we choose to use Dataiku for deployment. So we continue to write our own code and to use Dataiku for deployment. Why? For different reasons, because AutoML, it's like sometimes like black box, and also because there are some methods and some approaches that we wanted to implement that they weren't available in DataIQ. For example, the SMOT method wasn't in DataIQ. If you do pre-processing and you want to input missing data and use, I don't know, Canon or something like this, there are not a lot of imputation method on DataIQ. Even to have your own metrics. So in the machine learning part, to compute our own metric, we use the function make score of that exists on scikit-learn, and you can create your custom metrics and integrate it in the cross-validation part. So we choose to use DataIQ for deployment and to benchmark the algorithm with our own code. So if I have to explain this schema, so imagine that, sorry, no, for people, okay. C'est ça? Okay, boom. Imagine you have your training data, you have your testing data. So we choose our best model with the best hyperparameters, and we go back to DataIQ to re-implement the model, to retrain it on all our data set. And this is like it's the equivalent of point fit on Python, and this is the equivalent like I save my model on Pickle or JobLib. So once the model we train on DataIQ, we score it and we save results. So to finish about the machine learning part, so for the interpretability, we use SHAP values. So SHAP, it's a method that is inspired from game theory, and the goal is to compute the marginal contribution of each feature over all the prediction. This is not the real output of the SHAP value. I kind of recompute it to have percentage to be more understandable for the presentation. So our first important feature was the age of the pipes. The second feature, so the age followed by lags. So remember, we have time series because you have the pipes, its characteristics, and time series about if there was a leak or not these last years. So the second feature was the lags, the material. We have 5 types of material: the presence or not of clay, the diameter, the groundwater, and soil movement. And I think that's all for the machine learning part. Yes. Maxime will talk to you about business metric and
about
prediction.
the results. Yes.
Yeah.
So what we want to get with our model is a probability for each pipe to have a leak in the following year. And if you watch the previous slide carefully, you notice that an important feature was missing. It was the length of the pipe. And that is because we want to work with a linear probability. So because we consider that changing a longer pipe is more expensive than changing a smaller pipe, we can almost consider that it's linearly more expensive. We want to target the pipes which have the highest linear probability of leak in the following year. And for this, our hydraulicians provided us a formula to calculate this linear probability. And then we classify the pipes in 4 categories, from the most risky to the least risky. And we do this ranking per contract, because hydraulicians work per contract, they have money for their contract. And this is why we work per contract. And so the metric we use in this project, it's pretty important. It's a metric that is used in most ML and statistical tools to predict leaks. So basically what we do, we are going to check how many leaks we can detect in a certain percentage of the network. So, for instance, this is a network in percentage of length, very important. We don't reason in number of pipes, but we reason in length. And so we classify our network from the most risky to the least risky. This is, for instance, the 5% of the networks, the most risky to have a leak. And we count how many percent of the leaks we can find in this part of the network. So for instance, here, if we take the 30% of the network, the most risky, we can detect 60% of the leaks. And that's how we usually checked how many leaks we can find for the 1% of the network, the most critical, because there is not enough money to change 30% of the network. And so usually for 1%, we have around 10% of the leaks. So we do this curve by using a test data set. We use pipes that we don't use in our training. And so this is a web app. There's not an easy way to show it on the screen, but it's been developed in Dash. It's deployed on Dataiku, so it's pretty easy to deploy. We don't. The issues are handled by our DevOps engineer, and so basically they can choose their contract and they can display all the pipes of the contract. So in green you have the 60% of the length of the contract, the least risky. So every time you check a contract, 50% will be in green, and it's in red you have the 10% the most critical. So it's for the hydrologicians to use to check which sector is the most risky, where to look for leaks, and which pipes to target for leak detection. There are also a tool to download the score of the pipes to use in pipe renewal plans, for instance. And you also have a button to have the national rankings, because now this is a contract, 50% will always be green, but you don't really know how it does compared to the other contract. So we just did another tool that has a contract of the country. And for instance, if it's a contract where you have a lot of leaks, like in Agen, most of it will be in orange and red. And we also, our results are also displayed in an internal tool, but basically it's more or less the same of showing. Yeah, I see.
No. Apparently no. Okay. Technical problem, sorry. Okay.
It's good?
Yes.
Thanks.
Simon?
Wow.
Okay. So we achieved our first outcome. That's to provide our first results to our colleagues on the field. And what's next? We have a lot of things to do next. So we want to work on monitoring the model in production and having, for instance, we don't have metrics to follow our model in production. We want to work about managing the data drift to see when our input data drift from the actual distributions. In perfect world, we want to study the model stability today. So the model is deployed on production, but we have a refresh of data every 6 months. and we continue to do some things manually. And what we want to do this year is to implement something that study the stability of the model, to retrain the model maybe, I don't know, every month or every 2 months, instead of waiting for new data every 6 months to retrain it. You want to talk about data quality?
Yes, we have a big problem of data quality in this project. So as I said, the pipe data is provided by the collectivities. And for instance, for pressure, we have like 10% of non-pressure, something like that. And it's a big issue, but because in research papers, you can see that pressure is a big factor in leak detection. So what we want to do is have a project that works, show it to the collectivity, say we have a project that works, and encourage them to provide us better data, so we can have even better results. Another part we want to do is automation of data acquisition, because for now we do it a lot manually on public API, so it takes a lot of time. And we have also a versioning issue that is linked to our usage of DataIQ, because it's not great with Git. So we basically work on a project without Git, and it's a bit of a mess sometimes. Okay. And we are done.
Yes,
Thank you for your attention.
Thank you so much for the presentation. So we have an audience on broadcasting that is thanking you for your presentation and is asking if it will be possible to share your presentation later on. You can answer later. So any question from the audience?
Yes. What was the period of your database?
Of our data?
Yes.
So we have 8 years of intervention data, historically. Yeah, it's from 2016 around. And since we use lags in our features, we check interventions on the last 2 years and a half. We can work with 5 years of data.
And did you find correlations between the model and static features, like maybe the clay? Maybe the movement of the clay is a large scale, like 1 or 2 years?
Actually, we use fixed data, open data, on clay and soil movement. It's fixed data. It's not data that evolves around over time.
Okay.
So for the characteristic data, so we have refresh each year, but for data that we used from an API, it's just fixed data that you have.
It's basically risky, regarding to clay, it's risky areas where you have a lot of clay, medium areas, and less risky areas. It's not temporary.
No. Yes, we have just information if there is clay or not. Yes.
Yeah.
Even I think for soil movement, it's the same. We have just information. Huh?
You have to ask Amir.
Yes, Amir, yes. Where is Amir? Yes. We have just the information if there is soil movement around the pipes or not.
Okay.
Any other question?
Yes.
First, congratulations. What was the step of time of your time series, and when you predict leak pipeline, what is the step of time?
It's 1 year. We have information about intervention for 1 year over 5 years.
Yeah.
Yes, on total.
I don't know if it's a time series, but we have only 5 years, because we check every year will there be an intervention for leak in the following year. So yeah, it's 1 year step. So 5 years, we have only 5 years.
Do you have sensors distributed more or less uniformly?
Wow. No.
Sorry, I don't understand.
Do you have the sensors distributed more or less uniformly over the pipes?
If we have, if the characteristic is uniformed between the different pipes,
No, just the sensors like the
Yes.
devices. Do you have the
It's about.
I really don't know.
No, it's very.
I really don't know.
We only have a very few because it's expensive.
Yes, it's too expensive, so I don't know if it's
Yeah.
located uniformly or not.
Because we are not transporting oil, it's only water, so there is not enough money for. And it's an issue actually, because if we had it, there would be a lot less problems.
So you take like the difference of some quantities and try to figure out where you have the leak.
Yeah. We try to see how many water. It's not this project, but we can check how much water you put in the network and how much you consume. But the problem is that in France, a lot of the water check that you do at the consumer house, it's only done each year, so you can't really do much with it. So what we do mostly, it's we check the water distributed by night, because we consider that at night there are no consumers. So most of the water you put in the network is the water that you lose because of the leaks. And you check if the night is it's a night flow. If the night flow changes a lot, if you have a big variation in the night flow, that probably means that you have a leak on your network. And you do that by areas, by small areas. You divide your network in small areas, and in those areas you have input sensors and output sensors. And there you can check the flows, but only the flows that you put in the network, not the one you consume. And yeah, that's another issue.
It's another use case that
Yeah.
maybe we can present next time.
Did you define any KPIs to evaluate the value of the final product?
So no, actually, the unique metrics that we use, it's our business metric that we have developed with our hydraulic engineer. But next this year, we hope that we will have enough time to work about KPI and how to evaluate the model and how to evaluate also the product.
Yes.
Thank you very much.
Thank you.
So we'll stop sharing and then start sharing again. So.
Hello everyone. My name is Aliénor. I'm a data scientist at EDF, and I'm going to talk to you about a project I've done with Raphaël, who's an energy efficiency engineer at EDF and who's in the audience this evening. So thanks for coming, and thanks to all the audience. My talk will be about how we can try to improve energy efficiency in data centers through machine learning approaches. So first, we'll dive into the main points of my presentation. So we'll start with a short introduction about EDF and the context of our study. Then we'll explore the data and apply some statistical methods to address two challenges. The first is the identification of the parameters with the highest influence on energy efficiency. And the second is an attempt to quantify the impact resulting from different data center settings. And in the end, we'll discuss the perspectives. So EDF.
EDF is an electric utility company. It is owned by the French state. And we are one of the largest electricity producers in the world. We generate, distribute, and sell electricity to various types of customers, such as individuals, businesses, and industries. We have invested in new technologies for decades, for instance, in AI and data analytics. And we use it as a tool to make a better management and use of energy. EDF is also very committed to digital responsibility because one of our mission is to accompany the transition toward a low carbon future. And this brings us to the topic of today's presentation, so data centers. And so what are data centers? Data centers are big buildings that houses lots of computer servers, networking equipment, storage systems. And they are the backbone of our digital services. The applications we use every day rely on those data centers. However, they come with a high energy cost. At EDF, we have 2 data centers, and energy management is something that the operations team look closely after, especially in the pursuit of environmental certifications. We are certified ISO 5001, which means we try to make the best use of energy in our data centers, and we always try to make progresses. And the concern for energy efficiency is also very high today because of the context of high prices and also energy austerity, especially during this winter. But how do we measure energy efficiency? We use a metric called PUE, Power Usage Effectiveness, and it is a ratio. We divide the total amount of power used by the data center by the power of the IT equipment alone. So the lower, the better. The ideal PUE is 1, but of course we need energy to cool the system for lightnings, etc. So it is above 1. At EDF, so we chose a data center with a PUE of 1.6, but this number really depends on the choices of architecture and redundancy. The PUE can be influenced by lots of factors, such as the parameters of the cooling system, the outside temperature, the power of different computing rooms. So it is something that is hard to analyze. And that's why we'd like to do some machine learning to have a better understanding of which factor influence the PUE. And thankfully, our data centers are equipped with various sensors that collect data about their operations. So our question is, can we leverage this data to gain knowledge about the data center? And we've conducted 2 studies. So first, identification of the top parameters that influence energy efficiency, and second, the quantifications of the impacts resulting from one particular setting. Now we'll explore the data. So we have 2 years of historical data from the data center monitoring. It was extracted manually by the operations team. It was done for an internal data science competition. The data set is written in the long format, and it is sent irregularly to the system. So with this data, we'll address the two studies we've made. So first, identification of the top parameters influencing the energy efficiency. So you understand that we make some feature analysis to better understand the relationships between every parameter and the PUE. So the first step is to pre-process the data. When we transition from the long format to the wide format, since we don't have for each timestamp all the values of each parameter, we create lots of missing points. So we want to fill these missing points, and we do it with a time-based interpolation. Then we aggregate the data on a daily basis because we assumed it would reduce the noise. We have lots of parameters. It is 177. So, and there are highly correlated variables, redundant variables. So we chose with Raphael parameters that were different first and that made sense to him, that were interpretable. So we also calculated the PUE thanks to a formula that was given by the operations team. So in the end, we have a final data set of 45 columns and the PUE. Then we perform a feature analysis. We employ several methods because we want to limit the biases. Among these methods, we have the correlations. So the correlations can highlight linear relationship, like Pearson correlations, but also nonlinear relationships with Spearman correlations that are based on rank. Another method is the mutual information. So it describes a relationship in terms of uncertainty. Does the knowledge of one variable reduce uncertainty about the other variable? Feature importance is a technique that assigns a score to feature inputs, and based on how important they are to predict the target. So our target is the PUE. And last, lasso regression. So it's sort of a linear regression with regularization. And the most significant coefficients of lasso gives us information about how important this variable or this variable are. Let me show you the results for some methods. So here we are, the Pearson correlations. So on the x-axis, you can see the Pearson correlation coefficients, and on the y-axis, you can see the parameters. Sorry, I didn't want to write all the equivalences between the tags and the physical meaning, so I just make a comment about top parameters. Pearson correlation, so they range between -1 and 1. If it's close to 1, it means that the parameter and the PUE evolve in the same direction. Close to -1, it's the opposite. And close to 0, it means that it's not correlated. So with this method, our top parameters were the outside temperature first, and then a special cooling unit, we'll talk about it later, and a ranking of powers of computing rooms. Another method is mutual information. So it ranges between 0 and 1. 0, it's not, we don't have information about the PUE knowing one variable. 1, we know everything about it. It's based on entropy. And with this method, our top parameters are more or less the same as before, just we had several sensors outside, so they are reversed. So not a lot of change. But with Lasso, it is a bit different. Lasso deletes highly correlated and non-significant variables. And here the ranking is different. So it highlights the importance of the temperature of water at the output of cooling units. So it's the top parameter. And then we have the same ranking, so outside temperature and hours of cooling units and computing rooms. So to recap with most methods, the biggest predictor of the PUE is the outside temperature, followed by a ranking of powers of cooling units and computing rooms. But something was very interesting. We saw that a particular cooling unit appeared particularly high in terms of absolute value. And we are thinking why. And Raphael checked and saw that there had been leaks during the time of our study on this particular unit. So statistical indicators, even they seem dry in the hands of experts, can lead to interesting discoveries. One last point, so Lasso showed the different ranking, and we now focus on this parameter, so the temperature at the output of the cooling units. Of water, of course. So it's interesting to state that one variable is important, another is not, but what's more crucial is trying to quantify the impact on a special setting. So the operations team had an idea. They wanted to increase by 1 degree from 8 to 9 degrees Celsius the water at the output of the cooling units. And they told me, can you quantify what it will do on the PUE? So I said, I'll try. That's what I did. So I built a machine learning model to predict the PUE based on several factors, including, of course, the one we're interested in. And then I vary this parameter and observe results on the PUE. So first step, train the best model possible. And to do so, we have to do some pre-processing. So again, there was missing data. Again, I filled missing data. I tried different time aggregations based on a daily or hourly basis. And this time I use all the parameters, so not only the one I had chosen with Raphael for the previous study, because I wanted more performance. So I used PyCaret, which is a Python library that automates machine learning workflows to make a short comparison of the two data aggregation, so on a hourly or daily basis. And with PyCaret, I saw that the aggregation on a daily basis provided a better result, so I chose it. But it also created problems because when you do it, you have less data. So I performed feature selection. I used the lasso technique. But with 177 parameters, the temperature of this water was not that important. And we also had two sensors on chain A and chain B because we have two groups of cooling units, so we have two temperatures. So I had to keep, unfortunately, lots of variables. I used PyCaret again to choose the best algorithm, and I double-checked with cross-validation and scikit-learn. So the best algorithm was Bayesian ridge regression, which is a ridge regression with Bayesian inference. So we don't try to minimize the loss, but to maximize likelihood. And then I made some hyperparameter tuning with grid search. And the final results on the test data set, so 30% of the total data set, showed these results. So a mean absolute percentage error of 0.6% and a root mean squared error of 0.01. So we trained the model. Now we vary the temperature of water, and it results in a decrease on the PUE, but it is very small. It is on the order of 10 to the power of -4. So this is too small. That's what we thought. We can see that the separations on this graph are linear, which is because we have a linear model, but it's not always the case. So a good practice is to use a partial dependence plots. And so for each row of the test data set, you keep all the variables except the studied one. You modify this variable progressively, and you predict the PUE. And then on the graph, you display the average PUE of each value of the studied parameters, but with an average that is made with all the rows of the test data set. This is because sometimes with certain models, variables can have complex interactions. So it is more reliable and less biased to take all the test sets. So to sum up, the 1 degree increase in the water, in the temperature of water at the output of a cooling unit lead to a small decrease of the PUE. What's interesting is that this method is replicable for other variables such as air humidity or lots of things. So it gives you a method to test some hypotheses, but without trying on the data center. An update has been made on the data data centralization tool. And it is interesting because now we have more reliable data and more regular data coming to the system. So there are less outliers, and it's I have less points to fill with missing value methods. What would be interesting would be to make a variation of the power of pump at the same time, because in the data center we want to maintain a certain temperature so that the servers can work well. And when we increase the temperature of water on the cooling units, then we have to give more power to the pumps, because otherwise the temperature in the data center would increase. So if we make those simultaneous variations, is the PUE higher or lower? So I think we will continue working on it. So these two studies had a goal. We wanted to show that data-driven approaches could help find ways to improve the energy efficiency in data centers. So now with Raphael, we're working on the model quality and its impact. We want to use more basis data center settings so that the variables are more independent, resulting in better modeling, but also on a more useful simulator, because we choose this parameter so that because we know that the operations team can make modifications on it. So one question is, can we take this work and create a generic product out of it? Not exactly, because all data centers are different. So we have to retrain the model to have an accurate simulator, but the general ideas remain. So it can inspire energy efficiency actions in every data center. So thanks for your attention. That's all.
So just so apparently there was a problem with streaming, and the audience only saw your first slide. So, but it's okay, no problem. If you can share your presentation, I think
Okay.
we can
I'll
solve it
send it.
later on. So
It's
it's
interesting.
okay. Yeah. So yeah. Any question, please?
So I have maybe one. Do you have any, so there is actors like OVH or Scaleway, which also have data centers. And sometimes they are publishing like data with PUE and stuff like that. Do you know if factories have like open data set that you could try to replicate basically the work that you do here or there?
It's something interesting, but we haven't tried. I don't know if you...
No.
We can also ask questions to Raphael, which is our data center expert.
Yeah, I have a question. What is the range of temperatures you have when you train the model? Because we did a similar experiment with a totally different case, and we noticed that it works, but like if the range of temperatures you have where you train is different than the range of temperature you're trying to predict, the model can just say something that maybe it's extrapolated. So if you don't have like 8 degrees in your training data, maybe the model is not really
We
able
had
to.
8 degrees, I think, but we had from 6 degrees to I think it was about 9 degrees. So there were slight variations.
How did you choose your time interpolation method? How
Sorry?
did you choose your time interpolation method? Because you had irregular data and you had to choose some
Yes.
interpolation.
So we didn't have at the time of the modeling all the information. So I thought that the safest method would be to make a linear interpolation between two values of a data sensor, and that's what I did.
Okay.
Other questions?
Why do you think?
Okay.
Why do you think the Bayesian ridge regression method
Works
the best
well.
in
Yes,
this case? Why is it?
I read this on internet because it seems that it works well with when we have insufficient data. It makes statistical, I think, assumptions, and I think the model doesn't work very well. We don't have enough data with too much variables, but it was just to show what we can do to test some variables, but we have to improve our model, more data, less variable.
Yeah, so with the lasso, normally the coefficient that you get is kind of telling you, so it's linked to basically the variable that you want to predict as well. So the value of the coefficient have values that could say if I increase 1 degree of that specific variables, that will have this impact on the PUE, which is actually the experiment that you do afterwards, like the second experiment. Did you check if actually what you find in the first experiment and like the values is actually what you find out afterwards?
No, I just used it for feature selection, but it would be a good idea to compare the results.
Okay.
But you don't really know if the first method, lasso, has good results. So there is also bias in doing it.
Yeah.
But it gives you an idea. Other questions? Oh, so
Thank you so much. Thank you for following us online, and thank you for being here. So just a quick announcement, thanks to Coiled, we have some goodies and some t-shirts at the back of the room. So if you are interested to just go and pick one. So thank you.
Thank you.
We go to the, yes, I just for the.